So continuing our discussion of hydraulic systems, we left off here where I had some examples or an example of a full aircraft hydraulic system. Now, there are actually three hydraulic systems shown here. So remember, there's a left, a center, a right. In this case, some aircraft, they call them 1, 2, and 3. And usually if they're 1, 2, or 3, it's usually 1 is left and 2 is right and 3 is a center type system. If it's an Airbus, it'll be blue, green, and yellow, and I can't remember which one is which, left, right, center, but blue, green, and yellow is what they use. So does some Embraers use the blue, green, yellow thing as well. So, but looking at them, you know, this is the same aircraft, just looking at each kind of systems individually. So again, just a few things to point out. We're going to have a reservoir that's going to hold our fluid. From that reservoir, we're typically going to go to two different pressure sources. In this case, we have an EDP. What's EDP stand for? You remember? Engine-driven pump, right? Yes, engine. And what about ACMP over here? AC motor pump, right? Because the AC aircraft, these are going to be AC pumps. They're a full three-phase pump. Some of them are upwards of 60 amps. They're pretty high. They can draw a lot of current on big aircraft because they're converting a lot of power into a lot of energy into hydraulic power to power, you know, things like landing gear. You know, some of the biggest loads on your airplane aren't your primary flight controls, but rather when you go to extend or more importantly retract the landing gear, that takes a lot of fluid. Flap systems usually are pretty hydraulic intensive if they're a hydraulic flap system. And so systems will be different sizes too. So your reservoirs, you know, some systems may have a much larger reservoir, other systems may be smaller depending on the capacity of all the items connected to it. So our two pressure sources, the primary fluid flow through them is the pressure outlet, which is shown in red here. You can see those. They come out, they go through some check valves, some filters. You can see the check valves and filters, and then they tee together and they form the manifold that goes out to the system down here on the lower right. And so in this case, this one is powering the thrust reversers, the brakes, the right system brakes, and the powered flight control system. So they got, you know, they just kind of grouped all the flight controls, you know, and it's a selection of flight controls. Some may control elements of roll, some may be controlling elements of yaw, some may be controlling elements of pitch, and some may be controlling secondary flight controls. So they just put them all in one box for simplicity's sake. From those flight controls, you can see in green, we have a return system. Return system goes through a filter and then back to the reservoir. If you also look downstream of the pumps in the manifold area, there's the relief valve here in the lower left. That sets, remember, your system pressure. So when the flow is minimal, the pumps can adjust their flow, variable flow, to do a low amount of flow, but maintain that 3 or 4 or 5,000 psi, depending on the design characteristics of the aircraft. And that is set by this relief valve down here. Then one other path we see in yellow here is we have a path that also comes off the pumps. It also has a filter module, and it tees together and goes to a heat exchanger. And that's what's known as, that is the case drain for the pumps. And so in hydraulic systems, the pumps, you know, they're pressurizing fluid, but there's a lot of spinning parts in there and things that are moving and sliding. They're piston pumps, so pistons are sliding up and down, things are spinning and rotating. So you need to provide lubrication to all that. And so the hydraulic fluid is used as the pump lubricant as well. So this is the fluid that kind of goes into the areas that it's not actually being like pressurized by the pump, it's going into the surrounding case, and it's providing lubrication. It's also going to be what carries away heat, provide cooling. So your main source of heat in a hydraulic system is not the things you're moving, it's the pump that's creating pressure, right? When we increase pressure, we're going to increase heat. And there's also friction that increases heat. And so the actuators and those don't really get that warm, but this is going to take the heat from the pumps, and that's why it goes through a heat exchanger before returning to the return side and back to the reservoir. Here's another aircraft. And the reason I show these, the big thing I want to show you is, again, just like with electrical and just like with other systems we're going to talk about, whether you're looking at a Boeing aircraft or an Airbus aircraft or an Embraer aircraft or a Bombardier / Mitsubishi aircraft or a Dassault Falcon or anything, their hydraulic system makeups use all basically the same components put together in roughly the same configurations. Okay, where we have a reservoir going to our pumps and more than one pump per system, going through filters, going out through a manifold to various items. Now this one doesn't show the return path, but there's going to be a return path. This one also doesn't show the case drain, but there's going to be a case drain. Okay. Here's another version. Again, this one just shows the pressure path, not the return path. But again, a reservoir, 2 pumps per system, typically 2 different power sources. So, here, engine-driven pump, AC motor pump. On the left, engine-driven pump, AC motor pump on the right. Center system, 2 AC motor pumps. Because most of these are twin-engine aircraft that I'm showing. But with AC motor pumps here, remember, left engine generator is going to be typically powering the left bus primarily. Right engine generator is going to be powering the right bus primarily. So one of these AC motor pumps in the center system is primarily going to be attached. It's going to get power from that left bus, and the other one's going to get power from the right bus. So even if you lose an engine, you have some kind of method to get power to all 3 systems. Same thing here. The engine-driven pump, on system 1, which is your left system, left engine. The AC motor pump for that, where do you think that gets its electricity from primarily? Gets it from the right engine. It's usually going to be powered by that number 2 bus. And in contrast to that, the number 2 system here, which is on the right engine, its AC motor pump is going to probably be pulling power off of AC bus 1, which is primarily powered by the left engine. Okay. Now, in electrical, we can connect those buses and we can move power. One engine or even an APU can often power everything if need be, depending on the size of the aircraft. Larger aircraft, maybe not. We'll have to load shed a bit. But, by having it that way, you've got that redundancy built in, right into whether it's through mechanical means, through hydraulic means, or through electrical means. Okay. Well, same thing there. So remember, our hydraulic pumps are taking that mechanical energy and creating fluid pressure through it. Those are getting that mechanical energy from somewhere else, whether it be an electric motor that's getting its power from a generator, that's getting its power from a mechanical source, that's getting its power from fuel, or directly from that mechanical gearbox on the engine that's getting its power from burning fuel. Okay. So we're going to convert energy to fluid pressure. Some of the pumps you'll see, hand pumps. We'll have a few of these on some, but not all transport aircraft, used as a backup or an emergency. Okay. The 727 we had 3 hand pumps under the flight deck floor to be able to pump the gear down in the event of a electrical hydraulic system failure. It also had a hand pump back in the tail area to raise the air stairs if you didn't have hydraulics available, if your airplane was shut down and you needed to close those rear air stair doors, that rear air stair door. Vane pumps typically are low PSI. We really don't have those on transport aircraft too much. They maybe occasionally have a use somewhere, but very, very rarely. Okay. Same thing with gear pumps. So you've seen vane and gear pumps. Those are more common in your small aircraft, your light aircraft systems, but not very common in these. The main pumps we're going to see are what are called axial piston type pumps. And these can do 1500 PSI or more. And specifically variable displacement, constant pressure. So I've got a few videos because trying to show or describe the operation is a little bit tough. I got a couple of videos here. I'm going to just skip ahead and then come back to the video. So here's a cutaway of what one looks like. So you have an input shaft that turns something called a swash plate. As that swash plate rotates, you can see the angle. It's going to slide these pistons either in or out of the cylinder block right here. And the fluid is going to get pulled in as the pistons, say this is rotating out toward, in the direction it's rotating here. right? The back side, I think, is going up. So fluid's going to get pulled in at the back side till it gets to the top. And then as it comes over the front, these pistons start to push back out. That's going to force the fluid out under pressure. So again, I have a video of that here. Okay. So here's a cutaway of the videos we just saw, and they discussed them. So, these are in the videos when we were talking about, you heard it talking about suction on these pistons, as they pull back or out of that cylinder block. They don't do a very good job of producing suction. These pumps are typically not self-priming, which means they can't get fluid moving through them if there isn't fluid already in them. And so they need some way to start the fluid into the pump. Once the pump is up and running, it's going to be able to pull that. But if the pump's filled with air, it'll cavitate, and all it'll do is basically push air back and forth and not do a great job of getting fluid going. It will eventually, but in that time that it's cavitating, it can actually cause damage to the pump. So most of these pumps are going to have some method in order to increase or in order to help kick off the flow of fluid. Yeah. Yeah, it can be. Yeah, but some are better, like an impeller pump, they tend to be more self-priming than a piston pump, for instance. So, but even those you need help. I have an impeller pump on like my pool, and I have to pour water in it when the system gets drained to get it started again. I gotta like open a cap and run a hose in it to get it running again. But that's because it's well above the level of the water, right? So it has to suck water up into the thing. But these are usually positioned below the reservoir specifically to kind of help with that. Other ways of helping with that is a lot of them, some of them, not so many anymore. Back, you used to have some that had an integral impeller, so that centrifugal type pump that does a better job of self-priming. What's more common is to have a reservoir that provides some kind of pressure on the fluid. So this pump is creating 3,000 psi. The reservoir might be putting about 15 to 30 psi on the fluid to force it from the reservoir out the tubes or lines that go to the pump. So here's a few views. Now this is a installed pump. I have a pump sitting here that I can pick up and kind of show you. And if people want to look at it or pass around later, you're welcome to do so. Oh, I'm running low on gloves. But here is my pump, and as I go through this, I'm going to point to different things on it. So here I've got the input shaft over here. This is an engine-driven pump that I have. If you have an electric pump, it's going to look very similar. It's just instead of having a shaft here that's like an engine, it goes into a motor, electric motor, or an air turbine, or a hydraulic motor, or whatever is going to drive the pump. One note: yesterday you guys worked on the filter. I said V-band clamps are everywhere. Here's a V-band clamp that would be on the flange here to mount it to the engine. So this uses a V-band clamp. No, there's a seal inside here at the shaft. So there's no fluid in this area, or there shouldn't be. If there's fluid in this area, it's actually designed to leak out, so so the seal's leaking. And if you get fluid in this area, you got to see if it's SkyDraw, the pump's leaking. If it's oil, the engine's leaking. If it's SkyDraw, the pump's leaking, and soon the engine's going to leak because the seals on the engine don't like SkyDraw. So you may as well replace both of them when you pull the pump off. But so the body of the pump here is, I'm going to set this down, hopefully everyone can see well enough, kind of in this area right here is where we have that swash plate, that, those pistons, the piston block, all that stuff. Over here, right here, this section, actually right here, they were talking about the compensator spring that controls the swash plate, how tight it is. That's this piece right here. So, and on ours, you can kind of loosen the nut up and then turn it and do it. Now, these are almost always set by the overhaul shop. If you're working on these out in the field, we never really adjusted this. Okay, if something wasn't working right, these were pulled off, because in order to properly adjust it, you have to have it hooked up to some pretty sophisticated test equipment. And so you can't do that on wing on the aircraft. But it's there, it comes, it's safetied from the, from the overhaul shop. Hopefully you don't have to touch anything with it. This right here is I believe this is a pressure sensor on this one, but it could, no, sorry, that's the bypass valve. So it's the solenoid bypass valve, which allows us to bypass the pump. In the lab, you did that. You press the button to, well, you did the shut off, never mind. And then I'll get into some of the other areas here in just a minute as we go on. So we have pressure going out to our system. On this pump, the pressure going out is plugged right now, right here. Okay. No, sorry, right here. It's got a side port, it's got the end port. So we've got a plug on it right now on the end of this ball-looking thing. This ball-looking thing is what's called an attenuator, okay? It's actually, when we get to accumulators, it's like a miniature accumulator. And its purpose is, if you can imagine the piston pump, even though it's spinning really fast, you're still going to get a little pressure spike every time one of those pistons, comes in front of the outlet port, right? And so these do create a pulsing in the fluid flow. And so this attenuator on the side here, not all pumps have it, some do, some don't. This attenuator on the side basically smooths out those pulses. Okay, that's why it's on the outlet side before it goes out to the rest of the system. So here's our outlet right here. Pressure out, right? And on our pump that's on the board here, you can see it's labeled, it's stamped in there. And this one is stamped to, right here, it says out. Okay. We have our inlet. On this one, the inlet is this big gold fitting right here. Okay. This is a self-closing fitting. When you remove the nut that goes on here, there's a check valve inside of here that closes. So there's our suction coming in. You can see the suction is larger than the output side. We always want to make sure we have enough fluid going to the pump that it has more fluid available coming in than what it's going to push out. And so your suction is typically your biggest, or your inlet. What do they call it on here? On here it just says in. Okay. On the one on the board it says inlet. Right. So that's your supplier suction. This, by the way, if you want to see this pump, this is the JT9 down in Hangar 1, the big engine in the back corner. So it's mounted to the side of the accessory gearbox facing out towards the hangar. And then we have a case drain line. Remember I said this case right here, this entire area is going to be full of fluid to provide lubrication and cooling for this pump. And so there's a small line right here. Little blue cap is on the one in my hand. The smallest line coming off here. That is the case drain. So there's going to be a certain amount of fluid flowing out of that while the pump is running. That had provided lubrication, had taken heat. That's going to go back. It's going to get filtered, going to go to a heat exchanger, and go right back to the reservoir. It's not going to go out to the system. Okay. Yep, and that one does say case drain on it. That one on there, that one's smaller, so it just says drain. But now, there are also 3 different sizes, so hopefully you don't swap, they're supposed to be dummy proofed. But if you dummy proof something, they're always going to create a dumber dummy. Yeah. It's all the same. So the fluid, the inlet here comes in. Most of it's going to get sent back out the pressure side. Some of it's going to provide the lubricating and cooling and then come out the case drain port. Yeah, so there isn't a separate coolant. It's all the same hydraulic fluid that you're using for both cooling and lubrication, as well as pressure. So here's the engine-driven pump. This same pump that was in the last picture. This is actually how it's oriented on the 747 engine, the JT9. It's vertical like this rather than sideways. Kind of sticks up. I just had to flip this picture so it would fit better. But this one's actually vertical. Okay. And you can see it kind of tucked in there, nice and tight. Now this is an older pump. If you look down on the flange here, you can see there are studs with nuts holding it on. Okay. This is a newer pump that uses a V-band clamp, typically. So most of your modern stuff has gone away from studs and nuts like that and gone to a V-band clamp. It's easier to get a good seal, and it's a more you know, because you're putting it on, it's creating that tension all the way around. It creates a nice even holding power. Whereas something like that, the flange can warp and stuff like that. So most of your accessories have gone to V-band clamps, and they're incredibly strong because you've got that tension all the way around. They're super, super strong. The weak point in them is this nut right here. Can strip if you over torque it. So hence the torque tap, torque tap. There you go. Here is another pump, more similar to the one I've got here. So that is a depressurization solenoid. This one has it. That's one way of shutting off. Your engine-driven pumps will have a depressurization solenoid. It's a way to shut off. It basically connects the suction and return side. And so any fluid that's being pumped just gets sent right back to the return if you don't want to send pressure out to the system when the engine's running. You just have to be careful with that because it also in many cases cuts off flow to the case drain part. So there's a limit to how long you can run it that way, or it limits the flow of fluid through the case drain. And so the pump can only run for so long in that condition. It's used in an emergency function. So I have this. This is a smaller pump than the one I've got here, 19 gallon per minute flow. You can see it doesn't have a pressure on there, right? They know how much pressure they can rate, but the pump isn't creating pressure. The pump is creating flow. Pushing that flow into an enclosed space is what creates the actual pressure. Here is an AC motor pump. So we have our pump and our electric motor. What is missing from this one compared to the last one I showed you? Nope, still has that. Yeah, the solenoid. There's no depressurization solenoid. Why don't we need a depressurization solenoid on an AC motor pump? What can we do? We just shut the motor off and it stops pumping fluid, right? So your AC motor pump is the same. It just isn't going to have the ability. It's not going to have an integral depressurization solenoid. You're just going to shut your motor off that drives it. Okay. Still has a, I'm going to say, suction pressure case drain. I can't remember exactly on this one which one's which, but this is part of an auxiliary system, so it's a very small pump. It's designed kind of as a backup. It was just an easy one to get a picture of. Okay. Here is the actual AC motor pump for the main part of the system. So this is a primary AC motor pump. So it's a little bit, but it's more tucked in, so it's hard to see. So again, we've got our electric motor, we have our suction, we have our pressure coming out, we've got a case drain coming out, okay, as well. This little line, I'm not quite sure. If I remember, it like lubricates the motor or something on this specific pump, but okay. We can also connect one of these pumps, and I didn't have a good one, so this is an old picture that I had. We can also use an air turbine to drive it. So we can take pneumatic bleed air from the engines, and we can run it through a turbine. So the turbine here is on the right. This is bleed air coming in at the top, goes through the turbine, spins the turbine. Here's the exhaust. And that's going to spin the pump that's right here and is really pixelated. So if anyone does an internship and finds one of these, please get me a new picture. Some of these are just old and I just haven't been around an airplane that had this where I could get a better picture with a newer camera. Give me a Polaroid. Shake it like a Polaroid. That came out when I was sitting in your seats, by the way, just to give you, if anyone listens to that. Outcast was big in the early 2000s. So here we have a ram air turbine. We saw a similar setup with our, and I'm just going to go ahead one. We saw a similar setup, and again, you can see I have not been able to update this picture because I haven't been around an aircraft that has this. So again, if you're interning anywhere, or once you graduate, if you get a job somewhere, and you work on particularly 767s, I'd love you to get pictures of these things for me and send them my way. But here we have a ram air turbine, just like we had on our electrical generator, right, our emergency generator, hooked to a hydraulic pump back there. Now, most of those don't have 3 lines necessarily. They may only have 2. They may not have a dedicated case drain because they're not going to be used very long and they're not going to be putting out tons of heat. They're still going to lubricate, but that fluid's just going to kind of get mixed in. But yeah. So those are kind of our, so, AC motor pumps, engine driven pumps are going to be our main pumps. Air driven hydraulic pumps can be main or auxiliary. They're usually more of a demand pump, right? The 747 you guys are working on the sim, it has AC, or it has air driven hydraulic pumps as demand pumps on 2 of the systems. The other 2 systems are electric. The 747 does not have a ram air turbine hydraulic pump. In fact, there's not a lot of aircraft that do. But like I said, 767, and you want to work on those, get me a picture of one. I'd appreciate it. So, and I don't have AC motor pumps here because they're basically the same thing, just with a motor attached. So I'm not going to bring a whole bunch of different ones. We didn't pull them all out of the 727 when we took it apart. This right here is something called a power transfer unit. And a power transfer unit is, they can be 2 hydraulic pump / motors connected together, or in some cases, they're a hydraulic motor and a hydraulic pump. A hydraulic motor takes hydraulic pressure and causes it to spin. So we use hydraulics to drive a motor versus, it's basically a pump operating in reverse. They're a piston, they're pistons, same thing as, they look internally pretty much the same as this. The one caveat, the one difference is that swash plate is in a fixed position. They're not variable. Okay, so they have a fixed position, fixed angle of inclination, and you send fluid in one side, that pushes the pistons, causes it to spin, fluid comes out the other side. And that rotating motion can then be used to drive something. So we take a hydraulic motor and we drive something else. Yeah. No, it's a motor, so it's not creating pressure. If it's driven the other way, these are another backup where they're pretty much going to be a constant displacement. They're designed just to provide a small amount of fluid to operate like maybe landing gear extension. So these are installed. They use pressure. The key is they use pressure from one system to generate pressure in a second system. And so, in fact, some of those diagrams I had, let me do a quick run backwards here. Here we go. So here is a power transfer unit at the bottom right here. So what this allows is, in this case, this is a directional one. It can only go one way. It allows us to use hydraulic system 1. If we open this PTU selector valve, that sends power to the power transfer unit. So that spins. This is a motor essentially on the left. A pump on the right. That pump is going to send fluid. And you can see here's this PV is a check valve. Okay, so it won't send pressure up, but it'll send pressure down to power the landing gear in an emergency. So if we lose, in this case, system 2, if we can't power up system 2, we can use system 1 to power the landing gear, to extend the landing gear, to run the brakes, to do that kind of thing. Okay. These replaced, the 727 we had actually had a valve between the 2 systems that you could open, which is a lot simpler, right? You just put a valve in place of this and you just port fluid from one to the other. What's the problem with that? What's that? If you lose fluid in one system and then you open the valve, you're going to lose the fluid from the other system, right? So aircraft cannot have the ability to interconnect systems in flight anymore. In fact, the 727, that was really only meant for ground operation because it had 2 engine-driven pumps in one system and 2 electric pumps in the B system. They called them A, B, and standby. So the B system, you could run the 2 electric pumps on the ground, and then you could open that port to run the A system. And it was only supposed to be used on the ground, but it was a switch you could operate in flight. The other problem with that is that your B reservoir level would drop and your A reservoir level would increase because you'd be sending fluid to the other side and then it'd return. Now they had like an overflow that would send it back, but if we ran it too long, we'd end up with this big imbalance in reservoir levels too. So it really wasn't an ideal. So these PTUs replace that. think there's some others in here that have PTUs. I don't want to spend too much time looking through them, but I know that does. How many of you have flown recently? And this will see how much you pay attention when you're flying or care. How many of you have flown recently on an Airbus, like an A319, 320? Ever been on one of those? Anyone been sitting at the gate, they're boarding passengers, and all of a sudden you hear this weird growling, this pulsing growling. It's like, rrr, 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 rrr. Yeah, you guys know what I'm talking about? That is the PTU. The Airbus dog bark. That is located right in the wing section under the cabin floor. And that's the pilots testing it. It's something they have to test before each flight. So they make sure that it operates. They basically shut off one system and they test the other. So that's what you hear. And then all the passengers look around like, what the world's happening, right? They think it's this weird noise. Well, it's the PTU. It's the emergency PTU testing. Yeah, some do. Most don't. Most pilots don't even know what it sounds like because they do it up in the flight deck and they never hear it. Some are unidirectional, some are bidirectional. Everything I've shown is unidirectional, but there's no fluid exchange. That's the big key. We're not opening a valve between the two systems. So in this case here, you've got say like a pump driving a motor over here. This is not a case drain. This is actually if the seals leak on either of these, it drains this cavity inside of here. It's the same thing that happens on that pump. Like I was saying, if the seals leak, if it's hydraulic fluid, it's the pump. If it's engine oil, it's the engine seal. Okay. But you can see there really isn't a case drain. Again, these are not running constantly. They are a auxiliary or backup system most of the time. Okay, here's another one that was installed. Little grungier looking, but pretty much same thing. So this one is omnidirectional. It'll go either direction. This one is directional. You have a motor on the left and you have your hydraulic pump on the right. That's the one out of the 720. No, yeah, that's out of 727, and that was to run, it was a different, like it had that interconnect, and then it also had this PTU that ran like something, it was like a rudder backup system or something. I can't remember what it did exactly. Well, I worked for Eaton, and Eaton bought Vickers. So I think it was Eaton Vickers, yeah. I think Eaton bought it. So we're going to stop there because I don't want to get into reservoirs if we're not going to have time to really discuss it.